Hello, I'm Mohammad Etemad, a PhD candidate at Dalhousie University. I'm going to present a classification aid approach for trajectory segmentation called Wide Sliding Window Segmentation, or WS2. First, I talk briefly about trajectory segmentation applications. Then, we formally define the problem of trajectory segmentation. Then I discuss some available solutions for trajectory segmentation. After that, defining the problem, I propose or approach to solve this problem using WS2. At the end, I explain our experimental results and provide some conclusion on our approach. Trajectory segmentation is a preprocessing approach that can be used in a variety of applications. It can be applied to detect phishing or non-phishing activities. It can be used to detect animal migration and behavior analysis. In tourism, it can help identify points of interest and visit patterns. Trajectory segmentation can be applied to find segments with different transportation modes in traffic dynamics such as walk, run, bike, bus, or cars. This task can facilitate the identification of patterns in vessel movement, find abnormal movement, and planning for selecting an effective path in vessel navigation domain. We formally define trajectory segmentation as an approach to divide an ordered set of trajectory points called raw trajectories to subsets of ordered sets of trajectory points so that each subset satisfies a specific criteria. We evaluate the performance of the trajectory segmentation task by using knowledge of an expert represented in two variables called SID and label. SID is the segment identifier assigned by an expert, and label is the semantic knowledge about the segment, such as transportation mode or phishing, non-phishing labels. There are a few well-known solutions available for trajectory segmentation. The very first solution is based on finding stops and moves of a trajectory. This solution derives from the idea that there is a stop segment between every two moving segments. In this case, the moving object moves in the vicinity of a central point during a predefined time threshold. A more sophisticated approach to this problem is CB-SMoT, in which we define stop segments using the speed of moving object and utilizing a density-based clustering approach. GRASP-UTS is more advanced approach using the minimum description length (MDL) principle to find homogeneous segments. OWS is a recent approach based on utilizing a sliding window that uses an interpolation technique as its core to generate an error signal. This error signal is a proxy to indicate behavioral changes of the moving object. Here we are proposing WS2 including 5 major steps. At first, we generate an error signal, which is the core part of the OWS algorithm. Then we generate samples of error signal segments that are labeled by an expert. Using the generated samples, we train a binary classifier to predict if an error signal segment includes a partitioning position or not. Since we use a sliding window with size n, we have n number of predictions for each trajectory point. Using a majority vote, we decide if the potential partitioning position is an actual partitioning position or not. Then we select the partitioning position and produce our segments. In this illustration, we show the steps of WS2 in a big picture. This approach has two types of trajectory data. One which is labeled by an expert and another that has no label. Therefore, this approach relies on the quality and amount of available labeled trajectory data. The error signal can be generated using the same function for labeled and non-labeled data. Obviously, there is no labeled solution associated with each sample for non-labeled data. Using the labeled samples, we train a binary classifier and we use them to predict the label for each non-labeled sample. Then we apply a majority vote to decide which potential partitioning position is an actual partitioning position. As explained in detail in the reference 2, as a core part of the OWS, an error signal is generated using the distance deviation of interpolated midpoint from the actual midpoint in a sliding window over a trajectory. Here we can see a sample to produce an error signal for the green sliding window. The distance between actual midpoint, which is I4, and IC, which is the interpolated midpoint. IC is positioned using two extrapolated points, LB and LF, in a backward and forward manner. The use of two extrapolations in a forward and backward way helps to soften the error signal and provides robustness against some GPS noises such as jump noise and gaps. After generating labeled samples, we pass them to a classifier to learn to predict a partitioning position. We are not interested in finding the best binary classifier because we use a majority vote in our approach. All we need is a binary classifier that works better than a dynamic classifier. By increasing the length of our sliding window, the number of dummy classifiers used for the final prediction will increase, and it helps us to worry less about the accuracy of this binary classifier. We select a random forest with a limited number of estimators and features to increase the number of estimators participating in the final decision. We create labeled samples using the error signal generated for labeled data. Therefore, for each point, we know that if the point is a partitioning position or not. Here, we select a window size of 7 as an example. So each 7 error values create a sample E1 to E7, and the label is assigned based on the inclusion of the partitioning position. 0 is used for the cases that the samples do not include a partitioning position, and 1 used for the cases they include a partitioning position. To generate the next sample, we move our sliding window by 1 and repeat the above process to create the following sample. In the case of non-labeled data, we do not care about the label of each error signal segment because our binary classifier will predict it. For each midpoint of a non-labeled sample, we predict if the sample includes a partitioning position or not. Because each sliding window has n trajectory points, we have n prediction for each window. The majority vote for each window produces the final decision whether the window includes a partitioning position or not. If the window has a partitioning position, the partitioning position is the midpoint of the window. Here we explain the majority vote in more detail. The decision to select a midpoint of a sliding window as a partitioning position derives from the predictions of all samples include the midpoint. Therefore, there is a number of forecasts for a sliding window size n. If the number of affirmative votes is more than n over 2 here, or degree of majority vote times window size, we select the midpoint as a partitioning position. The BCLS in this table is the result of predictions of the binary classifier, and the MCLS is the majority vote for that point. We use a parameter called degree of majority vote that indicates how many positive votes are required to accept a potential partitioning position as an actual partitioning position. When we decide which sliding window includes the actual partitioning position, we select the midpoint of that sliding window as the partitioning position, which is the last point of a segment. The next point is the start of the next segment. We have developed a state point detection, SPD, CB-SMoT, OWS, and GRASP-UTS as our base to compare WS2 against them, since they are available solutions for this problem. We have employed 4 datasets in this research. Fishing, hurricane, and geolife datasets were applied to compare our proposed model with other algorithms. We collect and produce a dataset called a small AAS dataset, including the AAS data for 10 different vessels moving in the Halifax harbor to test our algorithm. We did not use a small AAS dataset for comparing the algorithms because it has been used in debugging and testing our algorithm. This proprietary datasets include 5,190 trajectory points and 153 segments, and included in the GRASP-UTS evaluation research. We clean this dataset by removing short segments shorter than a sliding window. This public dataset includes 1,990 trajectory points and 182 segments. The segments are created based on wind speed and the category of hurricane and introduced in GRASP-UTS research. This public dataset is a subset of geolife dataset, includes 32,095 trajectory points and 304 segments, and introduced in Microsoft Research. We select a subset of this dataset because GRASP-UTS took an unreasonably long time to process subsets larger than this, and GRASP-UTS was not able to produce the results for the whole dataset. We collected this dataset using AIS antenna and a Raspberry Pi. The data is shared with the AIS hub and is available on our GitHub address. We labeled some parts of this dataset using geographical features of the hardware and labeled them. This dataset is used in our debugging and testing of the proposed algorithm. Therefore, we did not use it for evaluations. There are two major parameters for WS2 algorithm. First, the size of a sliding window. Second, the degree of majority vote. We select 5 different sizes and 2 majority votes to tune our algorithm. Increase of majority vote shows more robust results and improved by increasing the window size. For hurricane dataset, the higher degree of majority votes provides higher quality segments. However, the increase of window size didn't increase the performance. We think this is because of the sampling rate in this dataset, which is 9 hours. For geolife datasets, shorter window sizes with higher majority vote degree provided more robust results. To compare the performance of our proposed method, we applied the harmonic mean of purity and coverage. Purity and coverage are introduced in GRASP-UTS research as a performance measure. Since they are perpendicular, if we assume there are no two adjacent segments with the same label, we also evaluate the purity and coverage independently, which are not reported in the paper and available on our GitHub page. As we can see, the proposed method provides higher performance than other methods on all experimented datasets. In summary, to our knowledge, WS2 is the first supervised method for trajectory segmentation. It benefits from the majority vote to make more sound decisions on the placement of partitioning position and segmenting trajectories. Although this method has some strengths, such as its high performance and use of labeled data to learn and work in different domains, there are some weaknesses as well. First, the assumption of having access to labeled data is a limitation for this algorithm. Second, the algorithm cannot produce a reasonably good performance if the segments are smaller than the length of the sliding window. These are our primary resources in this presentation. There is more comprehensive list of resources available in our paper.